So if chemistry told you that like charges repel and unlike charges attract, well, repulsion and attraction should signal in you a fundamental quantity from first semester physics. What is attraction and repulsion? If I had to pick something from first semester physics as a way of describing attraction and repulsion. Go ahead. It's a force. So Coulombs Law is about force. That's what it is. Now, it's been a long time since first semester physics for some of you. Some of you, that long time is never. So if you don't know what a force is, it would probably behoove you to know a few things about force. Just simple ideas, childish words, like, can you give me a children's term that could be used to replace the word force? And anybody who was in my class last year better have it. What'd you say?
Push and pull.
A push and pull, that's right. So a force is a push or a pull. Now, we need more than that, because a push or a pull is what forces do. What do pushes and pulls result in? Motion. More specifically? Change in what? I heard the word, and I want to hear the word. It's important. Acceleration. Forces can cause acceleration. Newton's second law. Net force equals ma. This doesn't go away just because we're in electrostatics. It's important to understand that if you have an unbalanced force acting on an object, that object's motion will change. And I want to be very clear, you need to remember this, that they cause acceleration. They don't cause velocities, they cause changes in velocities. Particle can already have a velocity, it could have acquired that from something else. But a force can cause a change in velocity, that's the acceleration part. But the amount of acceleration, how much the velocity changes, that's tempered by the object's inertia. We measure inertia by measuring the inertial mass of the object. All review here. But if you didn't have a first semester physics, you need this. This is going to come up a lot, but it comes up frequent enough where you should have need to remember it. So a few other things. Inertia, we measure it in kilograms. Acceleration is measured in a combined term, that's meters per second, or meters per second squared. It's how much and how fast the velocity changes. So velocity is measured in meters per second. That other per second is a reminder that the meters per second is changing. It can be going from 5 meters per second to 10 meters per second. Right? That is a change in the object's velocity. Now, this gives us a combined unit of kilograms meters per second squared. And boy, you guys remember all the different possible ways that kilograms, meters, and seconds were combined last year? It felt like an infinite number. Remember, we get to start throwing in a C into all of this. And trust me when I say, when we start talking about things like henries and farads, you're gonna love looking back on the days when as hard as it was a joule or a watt. And hopefully you remember joule and watt from last year. Because if there's anything else that I think should be thrown into this, is that forces do a lot of things. Forces can change momentum. Momentum's its own physical quantity. Forces can change a particle's energy, which means we're talking about, again, introducing energy. Changes in potential energy, changes in kinetic energy. All the things that forces were responsible for last year are still responsible this year. So any one of those things can be thrown into this conversation. Forces also can cause a torque. Because of that, all the conversation about rotational motion can play in here. But last year, our forces really only boiled down to a couple of simple things. I can directly push on something, normal force. I can pull on something, tension. There were resistive forces like friction, and there was gravity, right? That was really about the limit of our number of forces. Well, I'm adding just one more to that list, the Coulomb force. So when I refer to the Coulomb force, I am referring to the force between charged particles, what you know as repulsion and attraction. So the Coulomb force is the force between charged particles. Now, this wouldn't be complete if I didn't spend at least a second or so reminding you that forces are directional. So we put a symbol here to remind us of that direction. In Newton's law, we say that the direction of the net force is in the direction of the acceleration. You know, it does come to my attention that perhaps I should also throw down a reminder of what that is, because some of you may not remember. Can some brave soul who I've not heard from tell me what that is? Go ahead.
It's the sum of forces.
Sum of forces. So I could have any number of forces acting. We would refer to this as the sum of forces, or I will often say, what other word? Net force. So the net force is a combination of all the forces acting on an object. So it's a lot to unpack. We spent weeks on it last year. I need you to call this to mind. So today, most of our attention is going to be spent on just looking at this in one dimension. Okay, but this is a three-dimensional idea. All good so far? All right. So let's take a few minutes and focus on the Coulomb force. How do we calculate the Coulomb force? You already have an idea about it. You know that one charge can interact with another charge. So we will always approach this only two particles at a time. Coulombs law only deals with two concentrations of charge at a time and is made to deal with only point charges. Things I will talk about in just a moment, but in your notes, the Coulomb force is made to deal with just point charges. We represent charge with either a lowercase or an uppercase q. And for this example, I'm going to use a lowercase q. And I'll explain when I use one versus the other here in just a minute. So the first thing we do is the product of the two charges. So obviously more charge gives you more force. If both charges are bigger, then we get more force. They're multiplied together. And this should look familiar because we had a similar force based on something like this before. While this is based on the intrinsic property charge, gravity was based on the intrinsic property of mass. So the more mass you had, the more gravitational force you had. Same thing here. Of course, what do you think could also influence how big that force would be between our two charges, Q1 and Q2? Yeah? Yeah, how far apart they are. Do you think that our force would get bigger if they're farther apart or smaller if they're farther apart? Seems reasonable, doesn't it? Nature does seem to work that way. So your influence is greater the closer you are to the object. So something in the denominator here that could be used to temper the size of that force and be based on distance. And just like gravity, it is based on the separation distance squared. It is an inverse square law. But if you're paying close attention, you will realize that the top of this is in coulombs squared, and the bottom of this is in meters squared. But our final unit has to be newtons. So there is a constant of proportionality here, one to place it in the appropriate units. And it's the Coulomb constant, which we'll represent as a lowercase k. Now, writing it there is just fine. But your equation sheet has a tendency to write it as part of the numerator. It doesn't matter. You guys are smart enough to understand that that was written the same way both times. However, nothing on the top of this fraction conveys any means of direction. And we will have to be careful about direction in this class. So we are going to multiply by a unit vector. This is a symbol. And I've had a hard time convincing people of this. This symbol, bless you, has a value of 1. It is 1 long. So when you multiply anything by 1, does it change the value of the number you're multiplying? Right. It only conveys direction. And it says that it's in the direction of R. That's what it says. So it is the same R as we're talking about down here. But with that little hat on top, it's saying we're multiplying by something that is in the direction of R. So the force will be in the direction of the separation distance. That's what it's saying. Now, to put this into context, let's get a picture in front of us. Let's say that I have a point charge here and a point charge here, and they are both, for the time being, positively charged. It should already be clear to you that if I wanted to kind of get an idea in my head about how these charges were behaving, there's probably a force on this charge in this direction and a force on this charge in this direction, right? We know they're going to repel. Coulombs Law has to back this up, and it has to do so in a manner consistent with our argument for how Coulombs Law works. So I will draw first R into this. And I'll draw R as an arrow that points from charge 1 to charge 2. This represents R. So this is charge 1, this is charge 2. This green arrow represents the force on charge 2 from charge 1. Force on charge 2 from charge 1. Now just keep in mind, I am not going to use this kind of nomenclature for very long. I'm just using it to demonstrate how the R hat works, okay? Coulombs Law states that the force on charge 2 from charge 1 shall be equal to charge 1, whatever amount it is in coulombs, times charge 2, whatever amount it is in coulombs, divided by the separation distance squared. And here's the problem. The moment I square R, I strip away anything that has to do with its direction. So the directionality of R is gone when it's squared. That's what happens mathematically. I need to multiply this by a constant to bring the units in check. But then in order to make my force a vector, I say that it's in the direction from charge 1 to charge 2. I'm not going to put the 1, 2 there. I'm saying if we're interested in the direction of the force on charge 2, the direction will be in the direction from 1 to 2. Because it's particle 1 that's causing the force on particle 2. Does that make sense? So we kind of make particle 2 the origin, and we draw R from particle 1 to particle 2. So that's what's acting on it. Now, think about this in a better sense. If charge 1 were negative, what would that do to the direction of the green arrow?
Switch it.
Wouldn't it switch it? Well, that would also make this portion negative, right? Which would say it's in the opposite direction from charge 1 to charge 2, which is what we want. It switches the arrow, pushing it in the opposite direction of the red arrow. So if you multiply this out and your answer is negative, it's in the opposite direction of R. If you multiply this out and it's positive, it's in the direction of R. That's how the negative and positive is intended to be used. Again, negative and positive results in direction. Do we understand? Now that's going to play a role in everything we do. But for the most part, in these problems, you can reason out the direction of the force. Right? For the most part, in these problems, you know opposites attract and like charges repel. Because I did all of that talking only about this force. But you guys are shrewd, smart people. So you remember last year that for every force, there's an equal and opposite reactive force, which means this force has to be the same size, just in the opposite direction. That the forces on the two particles are of equal magnitude in opposite direction. That's why if it's an attractive force, they're pulled together. If it's a repulsive Well, that could be repulsive. If it was a repulsive force, it pushes them apart. I'm being very careful with the nomenclature and the symbology, but that's probably just for today. I think every other time you see me do this, I'll probably never write the hard hat down again. Because if we draw a picture, we can just draw the arrows in. And as you guys have come to know from last year, we get to choose what direction we call positive for our vectors and what direction we call negative for our vectors, right? And if it's on a number line, once we assign positivity and negativity, we can just look at the arrows we've drawn and look at the result of their direction when it comes to dealing with direction. Does that make sense? Well, we'll see. We're going to do an example in like literally a minute. So I want to see how we get so far. I want to add something to this, something I think you guys will probably want to know. Coulombs constant. Don't get too attached to this because we find later that Coulombs constant actually is based on something else. Coulomb didn't know that, but as more science went into discussing how this actually worked, Coulombs constant is going to change and we're going to express it differently. But for today, we're going to use this lowercase k as Coulombs constant. It is, for all intents and purposes, we don't need anything more accurate than this, 9 times 10 to the 9th, which makes it very easy to use. And the units are newtons, meters squared per coulomb squared. And that way the meters and the coulombs cancel out, leaving us with something that's in newtons. We can only take our particles 2 at a time. So in order to take our particles 2 at a time, I grouped them together. I did some color coding here. And I said that between the 2 particles that are closest together, I would calculate their force as 2 micro times 1 microcoulomb divided by the separation distance of 1 meter squared and times k. And that this force, since it's a repulsive force, would be pushing this particle to the right. Is that good? Any question about what I'm setting up there? Okay, again, you can only do this 2 particles at a time. So now I have to switch to a different pair of particles. So I bracketed the other 2 particles in yellow. They have a charge of 1 microcoulomb and 5 microcoulombs. Separation distance of 2 meters. I had to do that in my head. They're separated by 3, and there's a 1 meter distance on the one side, so I assume 2 meters on the other side. That's right, correct that. And then I square it, and multiply by my 9 times 10 to the 9th, but again, repulsive force, so that's pushing these apart. That's left, right? Now, you will have to decide whether left is positive or right is positive and add these together to get the net force and direction. Does that make sense? All right. I'm going to ask you to do a couple of these tomorrow while I'm out. Does that make sense? Bye-bye, everybody. Have a fantastic day.